Good morning all, how are you? Are you feeling a little Friday morning-ish? Because I certainly am. So today I want to have a look at these things. These are the supercapacitor protection boards, specifically designed for this type of supercapacitor. Actually, I'll get one out in a moment. I want to reverse engineer it, so I want to draw the schematic. And I want to try and find a position on this circuit for an LED, because this board has no indicator LED to indicate either when the protection circuit kicks in. Now, I'm not sure that this one kicks in suddenly and kicks out suddenly like the MOSFET and voltage detector ones do. I've got a feeling this one, because it's got a TL431, might kind of start working more gradually, but I'm not entirely sure until we get the circuit schematic drawn down. Now, I did put an LED on this one. You might be able to see that it's just sitting there between the legs of that transistor. And that's because I thought originally that would be a MOSFET, because on the supercapacitor protection boards for those cluster capacitor modules, they use a voltage detector and a MOSFET. But this isn't. This is a bipolar transistor, and I've connected that LED between base and emitter, which is never going to go over 0.6 volts, so that LED is never going to light. So certainly won't be doing that on the other boards. So why don't we start by trying to identify this transistor. But before I do that, I'll just switch this on because I want to charge this capacitor up. Now you can see I'm using 2 diodes. I don't really need 2 diodes. 1 would be enough. In fact, I probably could get away with none. I have charged a small supercapacitor on this power supply, this bench power supply. Now, if you're saying that's not a bench power supply, well, it is, because it's a power supply and it's on my bench. Yes, I've tried small supercapacitors with no diodes, but I quite like the idea of these protection diodes. There's no way that this capacitor can backfeed through the power supply. And the reason I'm using 2 is really purely for mechanical and connection reasons, because they just sort of fit. So that's charging at 2 amps. It's at 2.44 volts. Now, of course, the capacitor voltage is higher because we've got 2 Schottky diode volt drops there. So I'll just leave that charging up, and we'll take a closer look at this board. So this transistor is a D882. Let's grab a datasheet. And that, of course, means that it's a 2SD882. It's an NPN medium power transistor. There's the circuit there. Now, we've got a pin out here, but it's not for the surface mount one that's on this board. So I printed this one out as well. And that has got the TO252, which I'm pretty sure is the package type. And we've got, for the TO252, base collector and emitter connection information. Right, so let's draw that first. Now we can trace the tracks of these high power components. We've got positive going through 3. These are 1R2 resistors in parallel, so that's R400, so 400 milliohms, through into the collector of the NPN transistor, and the emitter goes down to minus of the capacitor. Now, can you see what's happening on this supercapacitor here? A blue light has come on, and it gradually fades up. This has actually reached 3 volts. It's in constant voltage now. So what's going to happen now, if I can get this to switch over, the keys have got nasty, is that the current is gradually falling as this thing sort of reaches its final absorption of energy. And this LED will get brighter and brighter. It's actually fairly dim because I've done a very crude connection of this LED to the capacitor circuit board. I've simply connected it across positive and negative, so it only ever goes up to 2.5 volts. It never sees more than that, so it never gets to a point where it's going to overcurrent. So is that the optimum position for that LED? Well, I'm not entirely sure. Right, so here we are. That's VCC. We go through the resistor first, and then we go into the transistor. That's NPN, isn't it? NPN medium power transistor, and that goes down to ground, which is there, GND. This is VCC. The voltage on the capacitor, no, not really, that's collector voltage. So this is R400, so it's 400 milliohms resistor, and this is the D882. Now the base of that transistor, which is the top leg, you can see just immediately goes to a via. Flip the board over and that goes to that short track. Flip the board back over and you can see the via emerge next to that component called 2TY to the center connection on 2TY. So let's draw that in. So if you do a Google search for 2TY, you fairly quickly come up, actually I did 2TY SMD, with this thing, the 8550 transistor, which I believe is PNP, and there it is, the marking 2TY. So I've printed out this data sheet because I just wanted the pinouts, and they're nice and easy on this. They don't have a silly 1, 2, 3, and then you've got to look it up in some separate table. Here they are, marked base, collector, emitter. Excellent. So on this 8550, which is a PNP transistor, we can see that the base of the 882 goes to collector of this 2TY, and emitter drops down here to capacitor positive. So I've added that onto my diagram, emitter of the PNP to VCC. The collector goes directly to the base of the D882. Okay, so what goes to the base of the 8550 PNP? Right, base of this PNP transistor comes around here. I believe it goes up and between these two pins of the TL431 and over to this bottom right hand corner. There's also a resistor here between base of the PNP transistor and VCC. Right, this resistor says 621, so 620 ohms. Right, so this is the TL431. Cathode goes directly to the base of the PNP. Anode goes down here to ground, I've determined. And then there's this programming pin, which you can use to change the reference voltage in this from 2.5 volts, which is the standard. Now, of course, this is a 2.5 volt supercapacitor here, so we're not going to change that reference. So I just want to check on this board whether that's actually connected up. And in fact, I don't know whether you can see this. Whoops. That reference pin, which is bottom left, goes off to two pads, one going down to positive, the other, where does that go? Yeah, that goes to negative. So the idea is that you can strap two resistors across there to change the voltage of this thing. They're not fitted on this board. You can see we've just got unfitted components there. So this is set to standard 2.5 volts. So I think that's actually the circuit. So I've been staring at this circuit, trying to kind of work out how it works, and I am struggling a bit. It says here that this is an adjustable shunt regulator. Now we're using this in 2.5 volt mode. There's no programming on this programming voltage pin. So what happens is when the voltage on the cathode becomes 2.5 volts more than the voltage on the anode, this thing starts to conduct. And the transition from non-conducting to conducting is quite sudden. There's quite a sharp change. It actually says that here somewhere. Yeah, a very sharp turn on characteristic. Now, if this turns on and starts to pull the voltage of this point here down below 2.5 volts, and you don't want this capacitor voltage going above 2.5 volts, I was thinking this transistor is only going to turn on when the base becomes 2.5 volts lower than the, 0.6 volts lower than the emitter, isn't it? So we need to develop a voltage across this 620 ohm resistor, or have I got that wrong? Will current flow emitter, base and down to ground through that path with this point at 2.5 volts? It's no good this point being 2.5 minus 0.6 because that's only 1.9 volts, or this would have to be 2.5 volts and this would have to be 0.6 above. So 3.1 volts. So yeah, struggling a little bit to understand how this circuit works. Now on this board here, as I say, I've just put a blue LED directly across VCC and ground. That doesn't go above 2.5 volts, so this blue LED is never going to conduct very much current. It's quite dim, but bright enough to see. And I'm just thinking that maybe, you know, I don't need to look into this any further. Just accept that it works. Leave my LED there across VCC and ground. And then I can see when these things are fully charged because they light up. When you get down to about 2.3, this LED goes out. My only concern about this is that LED going to pull the supercapacitor voltage down below what one of the capacitors with this protection board, but without the LED on, would drop to. So what I want to do is have one of these with the LED and one of them without, charge them both up, leave them for say 24 hours, and then measure the relative voltages of the two capacitors, because I quite like having this indicator LED, but it will be a bit of a problem if it just drains the energy out of the capacitor. Now you can see that this power supply has dropped to about 100 milliamps current just flowing through this circuit to hold that capacitor at the voltage. Well, 2.99, 3 volts is across this point here. This should be about 2.5 volts. But what I wanted to do was to take this above 3 volts. So that's the voltage. Let's take that up a little bit. Let's go, say, 3.1 and see what the current does. That's jumped up to 500 milliamps. And I want to see what that drops to as a sort of steady state. Because when I start taking this voltage on this power supply too high, this protection circuit should start to switch on and dissipate energy as heat, or power as heat, in that resistor and also this transistor. I did notice that the transistor seemed to get as warm, if not warmer, than these resistors. Actually, maybe I could get the thermal camera to check that. Right, let's have a look at the thermal imager. I've got 3.11 volts, 3.1 volts on there. It's drawing about 400 milliamps of relatively steady state current. So one would assume that's being dissipated in these components. So I've forgotten how this thing works. Right, we can see that there is some heat being generated on that board, but it's very hard to pinpoint exactly where it's coming from. I'm going to have to get very close, and of course it's all out of focus. I can't quite see whether that's coming from the transistor or the resistors. Let me see if I can get a better arrangement. Right, well, because of the difficulties with parallax, because of course you've got the thermal sensor there and the optical sensor there, I am only getting one blob of heat. So I put my finger on the transistor, so it would be that way up, and the transistor is warm. The resistors are stone cold, so the resistors don't seem to be doing anything like as much work, these resistors, as the transistor. The transistor is dissipating all the heat. That's quite interesting. And so with the power supply set back down to 3 volts across its output terminals, that's now only drawing again about 100 milliamps. If I put the thermal camera on there, the hot spot there is at around 31 degrees, so that's not a huge amount over ambient. Ambient is 19 or about 20 at the moment. Let's jack this back up. Let's look at voltage. Come on. Jack that back up to 3.1, where this will have to dissipate a lot more current. So that's 400. I'll just let this thing warm up a bit. And the hotspot, the highest temperature on here is this little number down here. It's not very easy to see. It's reasonably well aligned with the target temperature, but that's now climbing up 44 degrees. 45 degrees. So certainly it's having to dissipate a lot more energy into that transistor with 3.1 volts here rather than 3 volts. So the difference between 3 volts on this power supply and 3.1, bear in mind we've got these voltage drops, means that the protection circuit is starting to work, but most of the heat's coming in through the transistor, not those resistors. But as for a position to put an LED, even if it's red, I don't mind if it has to be a red LED, somewhere in this circuit. I get the impression in this circuit that unlike the voltage detector, which switched suddenly hard logic level switch and turned on the MOSFET on the other design, this one I think is a bit more subtle. I think, you know, currents sort of gradually increase. The current flowing through this 431 probably gradually increases. That gradually increases the current through this 8550 transistor. Yeah, I just can't think where I would put an LED. I did wonder whether I could actually put one in series with this line here, because this point here, the base of the NPN, will never rise more than 0.6 above ground. This transistor, when it turns on, will pull this point, well, if there were a resistor or an LED in here, pull this point right up to VCC. Would there be enough voltage? That would be about 1.9 volts. If I had an LED, and possibly I might need a resistor, but then that might affect the current flowing in through the base of there, and therefore the current flowing down here. Would putting an LED in this circuit upset its operation? It may well. So I thought I'd do some voltage measurements with the circuit obviously working and burning 400 milliamps. Voltage across the capacitor is 2.54, so it's a little bit higher than it should be, 2.5 volts, but I don't suppose that matters too much. Now I just wanted to check the voltage on the collector of this transistor, because if the transistor is doing all the dissipating, then it's probably a larger voltage across there and not much across those resistors. Let's try that, which is there. Right, yeah, so you can see that there's 2.4 volts at this point here, and 2.54 up here. So there's only 0.1 of a volt across the resistors, and therefore not much dissipation going on there. 2.4 volts across this transistor, so it's not really turned on much, is it? And so, of course, the current flowing through here with this large voltage drop, we've got a lot of dissipation in that transistor. I imagine if I pump more current into it, it will work harder and get hotter. I would have thought that voltage should come down. I suppose we could try that. Let's go to voltage and put that up to 3.15. Yeah, that's come down a bit. 3.2 could we try? That's come down a bit more, but what current's it burning? 1.6 amps. That's rather a lot. Let's bring that voltage back down to 3.1. See, I'm not sure whether this circuit can dissipate 1.6 amps. That could mean that the capacitor voltage starts to rise up. I suppose I could check that actually. Right, so with 400 milliamps, we've got a capacitor voltage of 2.54. Let's raise this voltage up. Actually, I suppose I could adjust the current limit. That would be better, wouldn't it? But let's just raise that voltage up a little bit. With an amp, 2.55. Let's go back to voltage. Come on. Let's go to 3.2. With 1.5 amps, we've got 2.56. So it is still holding the voltage down, but it's now having to work a lot harder, and presumably that will be getting fairly hot with that amount of current, because of course this current 1.5 amps is being dissipated in that protection circuit in order to stop the capacitor rising up to too high a voltage. It does look like it's creeping up a bit there, so let's come back down to 3 volts on the power supply, and now we should have next to no current flowing. Now it does say on the 2SD882 that it can have a high current up to 3 amps, but of course this hasn't got any heat sinking really, only what copper there is on this board, so I don't think it would be comfortable with 3 amps flowing through it. I'm not sure I'd really want to put more than, well, less than half. I think that 1.5 amps that we saw is probably about as far as you'd want to push that. So it's an interesting circuit because these resistors seem to do very little, and that transistor is dissipating pretty much all the energy when you attempt to overvolt this capacitor. In fact, if you think of the dissipation in this transistor in terms of watts, we had 2.4 volts across that transistor, very little voltage across these resistors. Now at, say, 1 amp, that would be 2.4 watts dissipated in this transistor. Well, that could generate enough heat, potentially, to get close to desoldering it. So if the transistor either burnt out or fell off the board because it desoldered itself, then it would no longer be protecting this capacitor. Yeah, I'm not sure I really like this protection circuit. I don't think it's very good. So I'm going to stick with this protection board because it's cheap, it's easily available. I've got 8 of them. They fit the capacitors, the bolt pitch is correct. But when I'm charging these capacitors, I'm not going to push them too hard because this protection circuit, well, particularly that transistor, does get very warm. So, right, okay, so with 100 milliamps quiescent current flowing through this circuit, so this protection circuit is probably just slightly on. The capacitor sits at almost exactly 2.5 volts, so that seems about right. Yeah, so I'm going to put 8 of these packs. I think it's going to be the 630 farad capacitors in series, making up a 20 volt supercapacitor battery in effect, or pack, series connected string. I'm going to have to think carefully about how I charge that string. Also going to have to think about what voltage I want to put into my amplifier. So there's all these sort of decisions to make. But just the next thing I'm going to do is charge one of these with the LED on up to 2.5 volts. That's my meter about to go timeout. And I'll do another one of these without the LED on up to 2.5 volts, and then I'll just leave them both for 24 hours, come back and measure their voltages. But I think that's pretty much all I want to do for today. I just really wanted to draw the schematic of this protection circuit, get some idea of how it works. So I think I'll leave it there. Cheerio.